I'll be talking a lot about arithmetic circuits. I think there was a tutorial yesterday so that you all know what an arithmetic circuit is. But just in case, like in the rest of the talk, I'll fix some underlying field f, and usually the field will not matter. If it does, I will mention it. An arithmetic circuit is computing a polynomial in over the field, starting from variables, field elements, by terms of the basic operations of addition and multiplication. So formally it's defined this. Size of a circuit is just the number of the operations. I should say that you don't really care about how the field elements are represented in this model, though in some cases you do care, and I will probably confuse the two. I mean, like, often you work over, say, complex numbers, and you don't care how to represent the complex number. You can have really transcendental numbers in your computation, and you still count them as having cost 1. The depth is the depth of the circuit, and formula is the circuit whose underlying graph is a tree. And those are the two interesting classes that we usually care about. There's the VP, which are polynomials of polynomial size and degree, and VNP are Boolean sums of those polynomials. And so now I'll move to something related to proof complexity, and the first one, the first topic is polynomial identity testing. So polynomial identity testing is the following problem. You are given an arithmetic circuit, and you want to know whether the circuit computes the zero polynomial or not. So this is one case where you obviously do care how the circuit is represented. So usually you think of the underlying field as being a finite field, which you can represent quite easily. Or you think about the rationals, where you think of representing the rational numbers in binary. Well, and there are things we all know about polynomial identity testing. I think there are people who know much more about identity testing than I do. But still, the basic facts are that the problem is in co-RP, and that follows more or less directly from Schwarz-Zippel lemma. So you know that if you have a non-zero polynomial and you evaluate it at a random point, then the polynomial will most likely not be zero. So that gives you a randomized algorithm for solving this problem. We don't know whether the problem is in P, and we don't even know whether there exists a sub-exponential non-deterministic algorithm for this problem, which is the thing that is interesting in terms of proof complexity questions. Maybe I should also say that the problem is interesting, and also its complexity is not known, even if you think about arithmetic circuits computing polynomials of small degree, such as when the circuit would be a formula, or where you would impose additional restriction that the circuit has, say, logarithmic depth, because the circuit of size s can actually compute a polynomial of exponential degree, which causes some extra things to worry about in the polynomial identity testing problem. But often you can think about f being a formula or low-depth circuit, and the problem is still unknown in terms of complexity. There are many interesting partial results. I will not mention all of them. Like, one important result is that if you can de-randomize polynomial identity testing, then actually you will obtain a new circuit lower bounds, which sort of explains why we don't know how to de-randomize this problem. And actually, even if you show that polynomial identity testing is in NP, say, you will still get new circuit lower bounds. The results in the positive directions in several restricted settings, like when you are thinking about non-commutative formulas, where you don't allow the variables to multiplicatively commute, or even branching programs, then you get polynomial time algorithm. And there are a lot of interesting results for sigma p sigma circuits, which are circuits of depth 3 and now you think about addition and multiplication gates as having unbounded Fedin. I'll mention those algorithms in a greater detail in a moment. So now the question then one can look at is the question whether, well, the most interesting question is whether polynomial identity testing is in P, but you can also ask whether polynomial identity testing is in NP. So in fact, what we want a polynomial size proof that demonstrates that an arithmetic circuit compute a zero polynomial. And this is a proof complexity question, basically. Like Tony has explained it before, but one can think of proof complexity as simply looking for NP algorithms for certain problems or showing that such algorithms do not exist. So basically, once you see a question is a problem in NP, it's a proof complexity question, because proof complexity is just about designing algorithms, non-deterministic algorithms for solving certain problems. So you can usually in proof complexity, you of course ask the question, is deciding whether a formula is a tautology, whether that problem is in NP, but you can ask a similar question for any basically problem whose complexity you don't yet know. You can make the question a little bit more specific, and you can ask whether you can efficiently prove that the circuit is zero by means of syntactic manipulations of the circuit. So by syntactic manipulations, I have like some sort of vague intuition what that should be, but I would assume that you take your circuit and you move things around according to like basic rules that multiplication is commutative, addition I guess also, so you can switch things, then you have some associativity things, and you will play with your circuit until you reach something which is zero. This is what I was doing most of my life before somebody no, but then they told me that Schwarzschild lemma is a better thing, but if somebody asks me like to show that the formula is zero, or in algebra usually that two formulas are the same, then you really like play with the symbols until you get what you want. So I should define formally what a syntactic manipulation is, but first like an example of an algorithm that I would consider syntactic, and that's this one. So you take your formula or circuit and you just open all the brackets and just check that everything cancels out. So that's a syntactic algorithm, I guess. It's not very efficient. Another syntactic algorithm, which is very nice, is based on the algorithm of Dvir and Špilka, and it concerns depth 3 circuits. So depth 3 circuit looks in the following way. It's a big sum followed by big product followed by a big sum. So it's a sum of products of linear functions. And you call the circuit simple if there is no linear function which divides every term in the circuit, and it's minimal if no proper subset of the top gates sum to zero. And you consider the notion of rank, and that's the rank of the linear functions appearing in the circuit. Now, a very nice theorem of Dvir and Špilka tells you that if you have a simple and a minimal circuit that computes the zero polynomial, then the rank of f is something. I hope that I wrote the bound correctly.
Doesn't matter, there are much better bounds.
There are much better bounds now, but I still like this bound because I like it. And
Thank you.
like this is why I was invited here, actually. But the point of this bound is that if you think of k as being constant, which is what it is used for, is that the rank of the circuit is much smaller than you would think. It's polylogarithmic, so it's small, which means that instead of in the previous algorithm, you just opened all the brackets in your circuit and checked whether everything cancelled. Like now, if the rank is small, you can first choose a basis which is a small dimension. You can think of those elements of the basis as independent variables and then open all the brackets. So, which gives you the algorithm. So first you switch to a convenient basis and then you open your brackets. And that gives you a quasi-polynomial time algorithm which works for fixed fan-in, for fixed stop fan-in. When k is fixed, this will give you an algorithm which is quasi-polynomial. Yes?
What's an example of a non-syntactic algorithm?
Okay. So for me, an example of a non-syntactic algorithm would be the following. So assume you have a univariate polynomial and you want to check whether it's 0. Let's say you know it has degree d, evaluate it on d plus 1 points. And if it cancels, if it vanishes on those points, then it's 0. So for me, I wouldn't call this a syntactic algorithm. Excuse me?
Looking at evaluations?
Yes. 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 Well, I should say, as Amir has said, like there are better algorithms known nowadays. So this gives you a quasi-polynomial time algorithm for fixed top fan-in. There are now polynomial time algorithms, but I still haven't made up my mind whether they are syntactic or not. This is why I'm mentioning this. I thought this is close to optimal. I was looking for it, and okay. So that
something like polycake log.
K square log d.
Okay. Yes. So there's no log d. If k is a constant, then instead of log d to k minus 2, it's like just log d. Oh, okay.
So for general field, it is K square log d.
Okay. Sorry about it. Okay. Yes. Yes. So yes. So let's think of k is equal to 3, and then. Well, now we'll give you like an ad hoc definition what a syntactic non-deterministic algorithm would actually be, and that's by defining a proof system for the polynomial identity testing. I will call it the PI system. Like in the original paper, it was called PFF, but it's hard to pronounce those bold P's and F's, so I will just call it the PI system. And the system manipulates formulas in this case. So you are supposed to prove that two formulas are equal or that the formula is equal to 0. So a line in the proof is just an equation that f is equal to g, where f and g are formulas. The inference rules that you use are the following, and the axioms are as follows. It looks like there are a lot of things, but if you look at it, then the inference rules are just basic logical properties of equality. So from if f is equal to g, then g is equal to f. Equality is transitive, that's the second rule, and it forms a congruence with respect to the basic connectives. As to the rest of the axioms, if you forget about it, well, this is also a logical axiom, but if you now forget about f, g, and h as representing formulas, those are just axioms of commutative ring with unity. So those are like your usual commutative ring axioms. And the last axiom just tells you how to handle the constants in the field. So this is your proof system, and I would say define that an algorithm, a non-deterministic algorithm, is syntactic if you can formalize it in this system. Of course, you can speculate about this, whether this is like a correct definition or not, because I can think of at least one rule that one can add to this system, which also looks syntactic, and it doesn't seem to be derivable in this system. But we can stick with this definition. A different version of the system, which is maybe a little bit more natural, is that instead of working with formulas, you will work with circuits. You will work with circuits instead of formulas. So the system, as I defined it before, works with formulas. So we are proving equalities between arithmetic formulas. In the circuit version of this system, you would work with equalities between arithmetic circuits. And the rules are the same, basically, and the axioms are the same, except you are working with formulas as with circuits as your basic objects. So one easy thing that you can see is that the systems are sound and complete. So you can prove equality between two formulas or circuits if the two formulas actually compute the same polynomial. This you can do by simply opening all the brackets and seeing that the two things are equal. And this is something that you can actually formalize in that system.
So we want to start with f equals g or f minus g?
So the proof starts with axioms of this form. Axioms of this form, uses inferences of this kind, and you are supposed to end with the equality f is equal to g. So you'll be working backwards.
So you start from the expansion of the polynomial, and then you write in the formula?
Yes. Yes, so we would start with f is equal to f, which would be the expansion of the left and right hand side, and then you will create the brackets that you are supposed to get at the end.
In different ways according to our formula.
Yes. Another thing is that I like to think about the two systems as an arithmetic analogy of the Frege system that Tony described and the extended Frege systems. So, in fact, you can show that if you work over GF2, then the Frege system is the same thing like the PI system when you add to it additional axioms that for every variable that xi squared is equal to xi, which tells you that you are working over Boolean cube instead of the whole field. Which somehow I think that the reason why we think about arithmetic circuits is that it's easier to work with arithmetic circuits than Boolean circuits. And the only difference between arithmetic circuit and a Boolean circuit is that in a Boolean circuit you use those extra axioms that tell you that that you are working over the Boolean cube. So you can think of arithmetic circuits as a relaxation of a Boolean circuit, relaxation meaning that you just drop the assumption that xi squared is equal to xi. So this proof system one can think of as a similar relaxation of the Frege proof system, where you again drop the Boolean axioms.
So in your proof, say when you do f plus g, can you replace it with a smaller circuit, or is it syntactic, or can you write it because to get
So you're asking, yeah. So for formulas, this is clear. Or is it not?
Yeah, formulas.
So when you work with circuits, you would have an extra axiom, say, that would say that if you would have an extra axiom which says that f is equal to g, whenever f and g you can open into the same circuit. So if you imagine that you expand f into a formula and you expand g into a formula, and you get actually the same formula syntactically, the same formula, then you will have it as an axiom. But you are not required to expand the circuit into formula. It's just assuming that you can expand it, you expand it. Yes, and this can be checked efficiently. So the question whether two circuits, when you open them syntactically, are the same, you can do it in polynomial time, because you will not open it, you will just check it with. And finally, the system, since I already claimed that the DS algorithm is syntactic, and this is supposed to encompass syntactic algorithm, then the system simulates the DS algorithm, because there's nothing really going on than just syntactic manipulations of the circuit. Well, and the open problem is whether either of those proof systems is polynomially bounded or not, by which I mean if you have a formula of size S or a circuit of size S, whether you can prove by a proof of polynomial size whether it's 0 or not in the system. So that's the main open problem here, and it's open even if you restrict the proofs to have bounded depth or actually, it's open pretty much in all cases that I can think of. Of course, one thing I should probably emphasize, so if you show that over a finite field, let's say, the system is polynomially bounded, then you will have shown that polynomial identity testing is in NP, because proof in that system is something that certifies that a circuit actually computes the 0 polynomial.
If you assume that the permanent is out and do the covenanting variation set and run this argument, can you prove that like Calculus algorithm does it work on this? Maybe Pavel Hrubeš.
Yes.
So what happens is that assuming that half polynomial exists and is permanent, then you know from covenanting Pareto to construct fitting sets. To show that those fitting sets give PAT, you need Calculus factoring, everything, etc. So just ask whether this all proof can carry out here and.
Oh, okay. So no.
Are you sure?
No, like 50%. No. I'm pretty sure I cannot reproduce this argument in the system, so I don't know.
And the bottleneck is what is?
I think it's the. So that's a good question, but so I think you cannot prove there is an added complication to all of those constructions that you have constructed, say, your hitting set, but you cannot prove, or at least I don't see any way how to prove in this system that the hitting set actually is a hitting set. Yeah, so I don't know how to do that. So often.
Pavel, I mean, in the slide, and you're saying PI can simulate DS. It's true in the sense that you just open it up, but we haven't proved that PI can. I mean, it's like the proof of correctness is still not in PI itself.
Yes.
No, just get the identity. I mean, everything comes out.
Yeah, but it's like somehow different because there's sort of the idea that it feels weird in the sense that here you haven't say the PI can simulate and it's efficient, but you haven't like the proof that that actually always works uses some external reasoning, whereas in the heating sets situation.
When I say that it simulates the DS algorithm, of course the system is too weak to speak about the algorithm. What I mean is that you can use the same algorithm to prove. So let's say this algorithm gives you quasi-polynomial upper bound on the length of proof of sigma p sigma, that every sigma p sigma circuit that equals 0 has a short quasi-polynomial size proof in this system. And you do it by using the algorithm as they do it. The system cannot say that the algorithm works, but it can, for every particular instance, it can actually run the algorithm and see that it works. And one another thing is that the bound on the rank, so the system doesn't have to prove the bound on the rank. The only thing that the system needs is that the bound is correct, which is that those guys proved, and the system will just guess the linear, the basis of the linear forms. It doesn't know that the basis exists, but it's promised to exist from elsewhere. It guesses the basis and then uses it.
The problem with the other argument is that if the circuit vanishes and all the evaluation of the polynomial, now you have to prove in the system that there is no short circuit forward.
Yes.
And
Yeah.
that's ridiculous.
Yeah. And,
So even if you assume it's hard, it's not clear you can prove that it's hard.
yes. Does it answer the question? Yes. So the reason why one would look at this system, I think there are several reasons. So one of them is it's sort of a simplified version of Frege and extended Frege. So one can think of it as a way of trying to prove bounds on Frege and extended Frege. But I should also say that the system has less rules than Frege, less axioms. So it's weaker in the sense that you cannot use the Boolean axioms that xi squared is equal to xi, but also the set of polynomial identities is smaller than the set of tautologies. So you are decreasing not only the expressive power, not only the proof power of the system, but also the expressive power, and it's not clear whether it's easier or harder to prove lower bounds on this system or not than Frege. It's quite likely that it's completely incomparable, which is different situation than in algebraic circuit lower bounds, because it seems strictly easier to prove lower bounds on arithmetic circuits than on Boolean circuits. Here it's probably not the case. It seems like a different question. The second reason is that it's a natural way sort of how to look at the complexity of the polynomial identity testing, and it would be nice to know whether you can have algorithms which are based on purely syntactic manipulations, because most algorithms that we know actually are not syntactic. And another thing is that the system can simulate, again in this weird way, a lot of results from classical circuit complexity. So so by simulate so the examples are the following. We all know that you can efficiently eliminate divisions from arithmetic circuits, and you can prove a similar thing in those systems. So basically, using division gates in your proofs doesn't help you too much. You can also show that circuits can be efficiently homogenized, and you can also show that circuits can be balanced. So there's this classical result, but by Valiant, Skeum, Berkowitz, and Rakov, that if you have a polynomial of small degree, which is a small circuit, then it will also have a small circuit of low depth. In particular, if you have a circuit of small degree, you can also transform it into a relatively small formula. Yes?
This syntactic versus semantic thing is exhausting. So here is an algorithm of a circuit, right? So you want to understand if a circuit is zero or not, if it's identically zero or not. So what we are going to do is do some variable reduction. We somehow prove somewhere that all variables except the first 5 variables can be replaced by some polynomials in the first 5 variables.
Okay.
And if the circuit was not identically zero initially, it continues to be not identically zero. Am I allowed to do this?
Well, it depends how you have proved that you can actually do it. So, like
But do we care about how? So what my algorithm would be that I'm going to replace x6 to xn by some polynomials p1 to pn in x1 to x5, and then I'm going to just expand out brute force and see if it's identically zero or not.
well, that to me looks pretty much like replacing x1, xn by like numbers and see whether the resulting polynomial is zero or not, which doesn't look syntactic to me. But the word syntactic is, I guess, confusing. But let's just make me the definition again. It's just the definition that like you can dispute, but I would define a syntactic algorithm that can be carried through in the system, in the PI system as I defined it. So like if you can carry your argument in the system, I would call it syntactic. But we can have an argument whether that's a correct definition or not. Like I just have this idea when I was at the high school and I was given an exercise like x plus y squared is equal to x squared plus 2xy plus y squared, and I was supposed to prove it, and I was sitting there and proving it, and that's sort of my so instead of syntactic I would say like high school algorithm. Okay, maybe that's a better notion. Well, and all of those things you can sort of simulate in the systems. By simulate, I mean you cannot, again, really talk about those results on a meta level. You don't have a notion of a circuit, but you can carry through all of those statements inside the systems. So basically, whatever you know about arithmetic circuits, like the classical results, then you can typically reproduce it in the systems. So Kaltofen's factorization I don't think I can do, at least. I'm not sure about it. I haven't checked it, but it seems non-obvious. So there would probably be exceptions to this statement. So just to see like how how this circuit balancing translates into the proof complexity setting, it would be the following statement. So it says that if you have a proof, if you start with a polynomial of with a circuit of small depth, and you have a small proof, then you can also find a proof which is still small, but every line in the proof has a small depth. So you start with a small with a circuit of small depth. You have created some proof that the circuit actually equals 0, and this tells you that by not increasing the size of the proof too much, you can actually assume that every circuit in the proof is shallow. So that's an analogy of the circuit balancing statement. So things like that you can prove in those systems. And this was, you can show that this actually implies that the PI system quasi-polynomial simulates the circuit PI system. Because remember the difference between the circuit version and the non-circuit version is that one works with formulas, the other one with circuits. So if you have a proof that uses circuits, you can transform it into a proof which uses formulas by simply opening the circuit into a formula. If you know that the depth is small, the formula will not be too large. Yes?
Earlier you said that over G of 2 you simulate things like extended Frege. So I think goes back to Amir's question from Tony Stark. I mean, you know, if you have a extended Frege thing, I mean, if you do that out, I don't see how having extended Frege gives you a circuit with low syntactic degree.
Yes. So
And this quasi-polymerization would require that. So I'm just wondering how these things fit together.
So that's a good question. So I said that the PI system is something like Frege and the circuit PI something like extended Frege. Now I said that those two things, on the arithmetic level you have quasi-polynomial simulation, so why don't we have quasi-polynomial simulation between Frege and extended Frege? So it's the similar situation like between arithmetic circuits, arithmetic formulas, and Boolean circuits and Boolean formulas. So Frege is obtained by adding the Boolean axioms as extra assumptions. It's very important that in this theorem you don't use any extra assumptions. So this theorem is just false when you add extra assumptions that xi squared is equal to xi. That's one issue. Another issue is that the degree, if you simulate extended Frege proofs, then the degree can be quite, if you think about it in terms of, well, I guess this makes sense only to you at this point, but the degree can be exponentially large. And here you lose a factor that depends on the degree. So that's another point where it breaks. And the third point where it breaks is that extended Frege or Frege cannot actually prove polynomial identities as far as we know. So there are at least 3 reasons why this doesn't work. And
So circuit PI always been circuits polynomially bounded degree.
Yes. So that's another good point. So as is common in arithmetic literature, I'm often thinking about circuits of polynomials of polynomial degree. But what I actually mean, so in order to make sense of this statement, so what you want to say is that you start with a formula, and so you want to prove a formula that, so f is equal to 0, and this is a formula. Now, in the circuit PI, you are allowed to use circuits to prove this equality. But and then you say that this formula, if it has a small proof in the circuit PI system, it will have a short proof in the PI system as well, which is okay, because you started with a formula which automatically has a small degree. So the degree of a formula of size s will be at most s. So this makes sense unconditionally. So when you are talking about simulation, you must start with something that the PI system itself can formulate, and that's automatically of low degree. But the point is good that so often we think about circuits of low degree, but there is no such restriction, arbitrary restriction on the circuit PI system itself. So this thing tells you pretty much nothing if the syntactic degree is exponential in the size of the circuits. So then this reduction becomes uninteresting.
You assume syntactic degree only on F, not on the circuit PI.
Yeah, that's another good point. Okay, so the size of the proof, the parameters that you have here depend only on the complexity, on the degree of f that you start with, because a priori you could, as your intermediary steps, you could use polynomials of much higher degree. But one element of this proof is that if you are proving equality of degree d, it's useless to use equalities of degree higher than d. It's the same thing like with arithmetic circuits, and that's actually one reason probably why arithmetic circuits are so nice as opposed to Boolean circuits, that if you are computing a circuit, a polynomial of degree d, you don't up to like a factor that depends on d, you don't really need to compute as your intermediary steps anything which is degree bigger than d. So Yes, yes. So the homogenization in particular tells you that you never need to exceed the degree of your polynomial in the computation. So this also tells you that in the proof, you never need to exceed the degree of the thing that you are actually proving. And so the bound depends only on the degree of the thing you are proving rather than on the intermediary steps that you might potentially use.
So moving from extended Frege to circuit PI, even if you get exponential degrees, you can use homogenization to push degrees down?
Well, the problem is, no, because extended Frege you obtain by adding those axioms that x squared is equal to x. The problem is that here you have degree 2, here you have degree 1, and it's not clear how you would homogenize this. So one problem with extended Frege, you can still think about extended Frege as working with polynomials and with those extra axioms, but then the notion of degree stops making sense really. It may be, and you cannot prove, for example, that if you precisely this statement, it would be the same thing like saying, even forgetting about proofs. So let's say I'm computing a polynomial of degree d over Boolean cube. So maybe it's much more efficient to compute it using polynomial of high degree. And this actually should happen unless like p is not equal to nc2 or something like that. So using high degree polynomials can actually help you when you are computing over the cube. And it can probably also help you when you are proving things over the cube.
So maybe one analog is that given an arithmetic circuit, we can compute the homogeneous components efficiently from it by homogenization.
Yes.
If you want to compute the multilinear part of it, for instance.
Yes, that cannot be done probably. Like the multilinear part is like sharp p hard to retrieve from the thing. So this, yes. So that's the this was applied. Oh, well, this thing was applied to prove to construct some non-trivial proofs of Boolean tautologies. The tautologies being, now we are thinking about Boolean tautology in this case, and this is one candidate how to separate Frege and extended Frege. Now I'm talking about the Boolean setting, and you can formulate a tautology. Let's say you think about GF2, that if you have two matrices that multiply to the identity, then if you multiply them into the opposite order, it also gives you identity. Now, this can be seen easily to have extended Frege proofs which are polynomial size, but it's not so clear to construct short Frege proofs. Now, this theorem can actually help you to construct quasi-polynomial size Frege proofs of those identities. I will not go into those details. It's just the point is that extended Frege and Frege are stronger systems than the PI systems. So first you work in the arithmetic setting where you have those nice reductions between things, and then at the end you switch to Boolean settings. More questions, because I'm ending with polynomial identity testing. Oh, great. So now we'll move to a completely different set of questions which are related to what Tony was talking about, and I'll call them ideal membership problems. So the general setting is the following. So you have a polynomial f which lies in the ideal generated by polynomials f1 through fk, and you want to certify that the polynomial actually lies in the ideal. So you want to ask what is the complexity of the polynomials g1 through gk, and I will call those polynomials as a certificate for f actually lying in the ideal. And you might guess that by the complexity I'll mean the circuit complexity. So I will make this definition, which I will be using quite frequently. That is, you will have the ideal complexity of f with respect to the rest of the polynomials is the smallest circuit complexity of the certificates g1 through gk. So I'll be using this definition again and again, so I think it's clear, but there are, of course, in general, infinitely many G's which certify that f lies in the ideal. And all of those G's can be computed in many different ways. So I'm just taking the minimum over everything. And you are also computing the G's simultaneously, which is usually just a detail. Another thing that I should emphasize is that arithmetic circuit, as I defined it, doesn't use division gates by default. So I'm not considering circuits with divisions, even though I mentioned that there is some simulation, but in this setting it's quite important that you don't have divisions. So now the first and probably the best known case of the ideal membership problem is the Nullstellensatz problem, which says that if you have polynomials which don't have a common zero over the algebraic extension of the field, then actually one lies in the ideal generated by the polynomials. There is also a stronger version of Nullstellensatz, which we are probably also all familiar with. This item is here mainly that if I run out of time is that I'm using the word proof here, so you can think about G1 through GK as a proof that there indeed are no solutions of the equations f1, fk is equal to 0. This equality is a polynomial identity, so we don't know whether this proof can actually be efficiently verified to be a correct proof, but you can do it at least randomly. So this is a randomized proof that is supposed to convince you that the equations have no solution. So as we are talking about the complexity, there is a bound which tells you that the degree of the polynomials G, it's actually never too big. And by too big, it is, well, it's exponential in n and k. Usually you think about a case when n is equal to k. So it's exponential in the number of variables, but it's not doubly exponential. The thing which was surprising about this result, I guess, is that before that people thought that the problem should be doubly exponential in the number of variables. So it's quite nice that you actually here get only an exponential bound. Yes, I'll also mention that. That thing relates to general ideal membership, when instead of having one lying in the ideal, you will have a general polynomial lying in the ideal, and then you do get doubly exponential bounds. And I think that was the reason why this was a little bit surprising. Well, and this is tight, so this exponential dependency on the number of variables is inevitable. You cannot do better than this bound tells you. So now I will remind you of this definition again. And there is an open question. So can you find a set of polynomials which have small circuit complexity? They have no common zero, but if you want to certify the fact that they have no common zero, you need circuits of superpolynomial size. That's the open question. I should probably say that there will be more open questions in this talk than actual results. But this question, it looks hard because you are supposed to prove some circuit lower bounds, and moreover you are supposed to prove circuit lower bounds on an infinite family of witnesses. So the polynomials G are not given uniquely. There are infinitely many choices that you can have. On the other hand, the g's can have exponential degrees. So it's not obvious to me that this question should be difficult. It's even possible it's an easy question, even though I don't know how to answer. Usually when you are asking questions like VP is equal to VNP, you work with low degree polynomials. Here you can take advantage of the fact you are working with polynomials of exponential degree. Maybe you can get good lower bounds in this case. I don't know.
You don't? I mean, if you allow like things, never mind.
What's the circuit? None.
Okay, and why, if it's, you don't have the Boolean axiom,
Yes.
so why is you cannot use just the lower bound you showed before, exponential, to show maybe not certain formula size only?
Yes. That's a good question. So another reason why this problem may be easy is that if you, instead of measuring the circuit size of the g's, you measure the formulas of the g's, you automatically get exponential lower bounds, because a formula of given size can compute only a polynomial of low degree. So once you are working with formulas, you get a lower bound, which is easy simply from the degree considerations.
Whatever was the example for showing a degree bound, the
Yes.
FIs there are very simple.
Yes, I think so, yes. Like I can, well,
Tony showed it, like x1 and
Oh, that the thing.
You have some
it's like squares here or something. But those circuits can be constructed efficiently, and actually the proof that Tony outlined here actually gives you the circuits. So once you sort of have an efficient sort of proof how to show that the formulas have that the equations have no solutions, it usually gives you automatically the construction of the g's. So you should be a little bit more creative than that. But I don't know how much more. It's and I think this is. Oh, sorry. One last slide, which is really unrelated to proof complexity questions, but you can also think about Nullstellensatz as a decision problem, which is usually phrased: you are given polynomials with integer coefficients, and you are supposed to decide whether it has a solution over complex numbers. The Collar's bound on the degree in the Nullstellensatz can be tweaked to give you a p-space algorithm for deciding this problem. And similar thing holds for any field. It really doesn't matter that we are working over complex numbers. But there is a very interesting paper by Koiran that if you assume GRH, just generalized Riemann hypothesis, it's actually the problem is in polynomial hierarchy. So the complexity of the problem is smaller. This paper is very nice, and this is a very interesting open question to actually place the complexity of Nullstellensatz into like the proper complexity class that it actually belongs to, and possibly remove the GRH assumption, and also to make this problem work over different fields than just complex numbers. Because like the question whether a set of polynomial equations have a solution in an algebraically closed field, it's a central problem, I think, in like mathematics. So it would be, I almost said in the real life. So in this book, yes. So it would be, it seems important to just know what the complexity actually is. So I think this is the time for me to stop for a moment. No, I'll be continuing in the afternoon.